The greatest integer function is a rule that takes any number and gives you back the biggest whole number that is still less than or equal to it. Think of it as always rounding down to the integer below, never up. We write it with special brackets that look like the bottom half of a box, like this, x. Because it pushes the number down to the floor, it is also called the floor function. For example, if you have 3.7, the integers below it are 3, 2, 1, and so on. The greatest of those is 3, so 3.7 equals 3. This is not the same as rounding to the nearest integer. Rounding 3.7 gives 4, but the floor gives 3. The greatest integer function matters because it chops the number line into intervals, where every number in an interval gets the same integer output. For a student learning calculus, this is one of the first functions that is not a smooth curve, it jumps. Understanding these jumps is essential for studying limits, continuity, and piecewise defined functions later in the course. It also shows up in real problems where you can only have whole units, like counting full hours or complete rows of seats. To find the floor of any number, imagine standing on that number on the number line. Now walk left until you hit an integer. That integer is the greatest integer less than or equal to your starting point. If you are already standing on an integer, you do not move, the floor of 5 is 5. Negative numbers can be tricky because less than means further left. For negative 1.2, walking left lands on negative 2, not negative 1, because negative 2 is smaller. So the floor of negative 1.2 is negative 2. This leftward walk is the whole idea. Suppose you walk into a shop with 250 rupees and each pen costs 60 rupees. How many pens can you actually buy? Dividing 250 by 60 gives about 4.16. But the shopkeeper will not sell you a fraction of a pen. You can only buy a whole number of pens, and you cannot spend more than you have. So you take the greatest integer less than or equal to 4.16, which is 4. You buy 4 pens, spending 240 rupees, and have 10 rupees left. The floor function naturally models any situation where you must take whole units without exceeding a limit. We already know the greatest integer function, written with these floor brackets. It asks, what is the biggest whole number less than or equal to x? Now we're going to draw its picture, its graph. Imagine plotting every input x against its output y. What you get is not a smooth line, but a staircase made of flat horizontal steps. Each step is exactly 1 unit long, and at every whole number, the staircase jumps up to the next level. The graph never goes diagonal, it only moves right, then jumps straight up, over and over, forever in both directions. Why draw this staircase? Because it shows us, in one picture, the most important behavior of the floor function. The output stays perfectly constant for a whole stretch of inputs, then snaps to a new constant value. This is what makes it a step function. Seeing the flat steps and the sudden jumps helps us understand ideas that come later in calculus, like limits, where we ask what value the function is heading toward, and continuity, where we ask if there's a break in the graph. The staircase makes those breaks obvious. It also gives us a visual way to solve equations and inequalities involving the greatest integer, just by looking at where a line crosses the steps. Let's build this staircase with our own hands, starting from x equals 0. Pick any x between 0 and just below 1, say 0.3. The greatest integer less than or equal to that is 0. So for every x in this interval, including 0 itself, the output y is 0. We draw that as a flat horizontal line at height 0, starting with a solid dot at x equals 0 to show it's included. But at x equals 1, the function jumps, the greatest integer less than or equal to 1 is 1, not 0. So we put a hollow circle at the right end of our step, at 1, 0, to show that point is not included. Then for the next interval, from 1 to just below 2, the output is 1. We draw a new flat step at height 1 with a solid dot at 1,1 and a hollow circle at 2,1. Let's see this staircase in real life. Imagine sending a parcel by post. The rule is, for the first 100 grams or any part of it, you pay 15 rupees. For every extra 100 grams, or any fraction of 100 grams, you pay 5 rupees more. So if your parcel weighs 50 grams, you pay for the first 100 grams, that's 15 rupees. If it weighs 120 grams, that's one full 100 grams plus a part of the next 100. You pay 15 for the first 100, plus 5 for the next part, 20 rupees total. The weight is our input X, in hundreds of grams. The cost is our output Y. For any weight from just above 0 up to 100 grams, the cost is a flat 15 rupees. At exactly 100 grams, the cost jumps to 20 rupees and stays flat until 200 grams. Every function has a domain, the set of inputs it accepts, and a range, the set of outputs it can produce. For the greatest integer function, written with those special floor brackets, you can plug in any real number you like, 2, 3.7, negative pi, 0. So the domain is all real numbers. But look at what comes out, the function always rounds down to the nearest integer. That means the only possible outputs are whole numbers like negative 2, 0, 5. The range is exactly the integers, a set of isolated dots on the y-axis, not a continuous smear. Why do we care about a function that jumps? Because the real world is full of sudden changes. Think of a parking garage sign, height limit 2.1 meters. A vehicle that is 2.09 meters fits, one that is 2.11 meters does not. That is a jump, a tiny change in input flips the output from allowed to not allowed. The greatest integer function is the simplest mathematical model of that kind of discrete, step-like behavior. It also gives us our first clear look at a discontinuity, a place where a function breaks apart, which is the central idea behind limits, the engine of calculus. Let's zoom in on what happens right at an integer, say x equals 2. If you sneak up on 2 from the left, taking numbers like 1.9, 1.99, 1.999, the floor of each is 1. So the left-hand limit, the value the function is heading toward as you approach from the smaller side, is 1. Now come in from the right, with numbers like 2.1, 2.01, 2.001. The floor of each is 2. The right-hand limit is 2. The function does not settle on a single value, it leaps. The size of that leap, the jump gap, is exactly 1. And this same jump happens at every single integer, all along the staircase. Imagine mailing a letter. The post office charges by weight bands, up to 20 grams costs 5 rupees, and every extra 20 grams or part thereof adds another 5 rupees. You have a letter weighing 18 grams. The greatest integer idea helps here. Divide the weight by 20 to get 0.9, and the floor of that is 0. So you pay for the 0th band, the base price of 5 rupees. Now add a few pages, the weight becomes 21 grams. Divide by 20 to get 1.05, and the floor is 1. You have jumped into the first extra band, so the cost leaps to 10 rupees. A tiny 3-gram increase doubled the price, that is the jump gap in action, and the same piecewise constant behavior we see in the staircase graph. We already know the basic staircase graph of the greatest integer function, x. Now we ask, what if we add a number, like x plus 2? Or what if we take the floor of x plus 3? Or multiply the whole floor by something? These are called transformations. They take a function we understand and tweak it, shifting it up or down, sliding it left or right, or stretching it vertically. The graph changes shape in predictable ways, but it keeps its staircase soul. We'll see exactly how each move changes the step heights and step widths. Why would anyone want to shift or stretch a staircase? Imagine a courier company that charges 30 rupees as a base fare, plus 20 rupees for each extra kilogram or part thereof. The cost function is a floor, 20 times the floor of the weight, plus that base 30. That base 30 is exactly a vertical shift, it lifts the whole staircase up. Or think of a bulk discount that kicks in after the first 2 kilograms, that's a horizontal shift, sliding the steps to the right. Stretching changes the price per step. Transformations let us take one simple step function and adapt it to real-world pricing, scheduling, or measurement problems. Let's build each transformation from the ground up. First, adding a number k outside the floor, like x plus 3, simply adds 3 to every output. Every step's height, the y value, goes up by 3. The step widths stay exactly the same, 1 unit wide. The whole staircase levitates. Next, adding h inside the floor, like x plus 2, is trickier. It shifts the graph horizontally, but opposite to the sign, plus 2 moves the staircase 2 units to the left. Why? Because the jump that used to happen at x equals 0 now happens when x plus 2 equals 0, so at x equals minus 2. The step widths remain 1. Now, multiplying by a number outside, like 2 times x, stretches the step heights, each step becomes twice as tall. The widths don't change. Finally, multiplying x inside, like 2x, compresses the steps horizontally. The jump that was at x equals 1 now happens when 2x equals 1, so at x equals 1/2. Let's solve a concrete problem. An auto rickshaw charges a flag-down fare of 50 rupees, then 15 rupees for every 200 meters or part thereof. What's the fare for a 1.3 kilometer ride? First, convert distance to meters. 1.3 kilometers is 1300 meters. The number of 200-meter chunks is the distance divided by 200, so 1300 divided by 200 is 6.5. Since we charge for any part of a chunk, we take the floor of 6.5, which is 6. The fare is the flag down 50 plus 15 times that floor. So 50 plus 15 times 6 equals 50 plus 90, which is 140 rupees. Notice the structure, the base fare is a vertical shift, the per chunk rate is a vertical stretch, and dividing the distance by the chunk size inside the floor is a horizontal scaling. The same method works for any step pricing, just identify the shift, the stretch, and the scaling. A limit asks, as x gets really close to some number, what value does the function get close to? It's like walking toward a spot on the floor and seeing what height the staircase step is right there. With the greatest integer function, written with these special floor brackets, the output is the biggest whole number not more than x. So at x equals 2.3, the floor is 2. But what happens exactly at x equals 2? The function jumps. To capture that, we use one-sided limits. We sneak up from the left side, where x is just below 2, and from the right side, where x is just above 2. If the left and right limits agree, the two-sided limit exists. If they don't, like at a jump, the limit does not exist. Why do we even care about limits with this staircase function? Because it's full of jumps, what mathematicians call discontinuities. At every integer, the function leaps up by 1. A regular limit that just looks at the value at the point would miss that jump entirely. The JEE exam loves to test whether you can spot when the left and right limits don't match. More importantly, this idea of checking both sides is the bedrock for understanding continuity. A function is continuous only if the limit equals the function's value, and for derivatives, which are limits themselves. If you can master limits with the floor function, you can handle any piecewise or jumpy function they throw at you. Let's derive this from the staircase picture. Take an integer, say 2. As x creeps toward 2 from the left, like 1.9, 1.99, 1.999, the floor of all those numbers is 1. So the left-hand limit is 1. Now come from the right, 2.1, 2.01, 2.001, their floor is 2. The right-hand limit is 2. They don't match, so the two-sided limit does not exist. We write dne. But if we pick a non-integer, like 2.5, the function is flat and constant all around it. From the left, x is 2.4, 2.49, floor is 2. From the right, 2.51, 2.6, floor is still 2. Both sides agree, so the limit is just the floor value, 2. The rule is simple: at integers, the limit fails; everywhere else, it's just the step you're standing on. Let's solve a concrete JEE style problem. Find the limit as x goes to 3 of the floor of x plus x minus 3. We can't just plug in 3 because the floor function jumps there. So we split into left and right. From the left, x is just under 3, so the floor is 2. And x minus 3 is a tiny negative number heading to 0. So the sum approaches 2 plus 0, which is 2. From the right, x is just over 3, so the floor is 3. Again, x minus 3 goes to 0. The sum approaches 3 plus 0, which is 3. The left limit is 2, the right limit is 3. They don't match, so the two-sided limit does not exist. The trick is always to handle the floor part by checking which step you're on from each side, and let the continuous part just approach its value. Imagine drawing a graph without lifting your pen. That's continuity. The greatest integer function, which we already know as a staircase, has a break at every integer. Between integers, like from 2 to 3, the graph is a flat, unbroken line, so it's continuous there. But at the integer itself, the left and right pieces don't meet, there's a jump. Differentiability is a stronger idea. It means the graph is not only unbroken, but also smooth, with no sharp corners or sudden jumps. For our staircase, the flat parts are smooth; in fact, they're perfectly horizontal, but at the integer jumps, the derivative simply doesn't exist. So continuity and differentiability are about where a function behaves nicely and where it doesn't. Why do we care if a function is continuous or differentiable? Because the main tools of calculus, limits, derivatives, integrals, are built on the idea of smooth change. The derivative tells you the slope at a point, like the steepness of a hill. If the graph has a jump, the slope at that exact point is meaningless; you can't draw a single tangent line touching a gap. If it has a sharp corner, the slope changes instantly from one value to another, so there's no single slope there either. For the greatest integer function, this means we can use calculus on the flat steps, where the slope is 0, but we must stop at every integer. Understanding where calculus breaks teaches us the limit of our tools, which is just as important as knowing where they work. Let's make this formal. A function is continuous at a point a if three things hold. The function is defined at a, the limit as x approaches a exists, and that limit equals the function's value. For our floor function at an integer, say 2, the left-hand limit is 1, coming from numbers like 1.9, the floor is 1. The right-hand limit is 2, from 2.1, the floor is 2. Since left and right limits differ, the two-sided limit does not exist, so the function is discontinuous at 2. Between integers, on an interval like 2 to 3, the function is constantly 2, so the limit at any point inside equals 2, which matches the function value. It's continuous. Now differentiability. The derivative is defined as the limit of the slope between 2 points as they get infinitely close. At a jump, that limit doesn't exist because the function lurches, so the derivative does not exist. Picture a taxi fare that charges $2 for the first mile, and then $1 for each additional mile or part thereof. The fare as a function of distance is exactly a greatest integer function, it jumps up at every whole mile. Between mile markers, say from 1.2 miles to 1.8 miles, the fare stays constant at $3. The derivative, which is the rate the fare changes per mile, is 0 on those flat intervals. You're not paying more for those extra tenths of a mile. But right at the mile marker, the fare leaps, so the rate of change is undefined, it's an instantaneous jump. This shows why differentiability fails at jumps. The idea of an instantaneous rates makes no sense when the quantity itself isn't changing smoothly. So the whole idea is, calculus works where change is smooth, jumps and corners are where it breaks, and the greatest integer function is a perfect, everyday example of both. We already know the greatest integer function gives a staircase graph, the output is constant over an interval, then jumps to the next integer. Many real-world rules work exactly the same way. A tax bracket charges a fixed amount for a whole range of income. Shipping cost stays the same for any weight between two whole numbers. A digital clock shows the same minute for 60 seconds, then flips. All of these are step functions, they are just the greatest integer idea wearing everyday clothes. The core is always, the input is grouped into chunks, and every input in that chunk gets the same output. Imagine you are mailing a package. The post office charges by the kilogram, but they round up, 2.1 kilograms costs the same as 3 kilograms. You want to know the price before you go. Or think about your phone stopwatch. It shows 0 seconds for a whole second, then jumps to 1. Why doesn't it show the time smoothly? Because digital displays count only whole units. The greatest integer function is the natural model for any situation where a quantity changes in discrete jumps, not smoothly. It answers the simple question, what whole number bucket does my input fall into? That is why this staircase shape appears everywhere, from tax tables to computer counters. Let's build each model from the greatest integer function. For a simple tax system, suppose you pay a base tax of 2,000 rupees for income up to 5 lakhs, then 4,000 for income between 5 and 10 lakhs. The base tax is just 2,000 times the floor of income divided by 5 lakhs, plus 1. For shipping, a common rule is, cost equals the rate times the ceiling of the weight. The ceiling is just the floor of the weight plus 1, because any fraction pushes you to the next whole number. For a digital clock, the displayed minutes are the floor of total seconds divided by 60. In every case, we take a continuous input, apply the floor function to chop it into integer buckets, and then maybe shift or scale to get the right output. The staircase graph is the fingerprint of this chopping process. Let's solve a real shipping problem. A courier charges 50 rupees for the first kilogram and 30 rupees for each additional kilogram or part thereof. You have a parcel weighing 3.2 kilograms. What is the cost? The rule means, for the first whole kilogram, you pay 50. For the remaining weight, you pay 30 rupees per kilogram, but any fraction of a kilogram counts as a full kilogram. So the extra kilograms are given by the floor of the weight. For 3.2 kilograms, the floor is 3. But the first kilogram is already covered by the 50 rupees, so the extra kilograms are 3 minus 1, which is 2. The cost is 50 plus 30 times 2, which is 50 plus 60, giving 110 rupees. Notice how the floor function naturally handles that part thereof's rule, it simply discards the fraction, giving us the whole number of extra kilograms. The floor function, written with these little L-shaped brackets around x, gives the greatest integer that is less than or equal to x. Think of it as rounding down to the nearest whole number. For example, the floor of 3.8 is just 3. The floor of 5 is 5 itself, because 5 is already an integer. And the floor of -1.2 is -2, because -2 is the next integer down on the number line. Its graph looks like a never-ending staircase, with flat steps that jump up at every integer. You can put any real number into it, so its domain is all real numbers. Why do we care about a staircase? Because the real world is full of stepwise rules. Think of shipping costs where the price jumps at each full kilogram, or tax brackets that change at whole dollar amounts. The floor function is the simplest mathematical model for any situation that changes in sudden jumps at integer boundaries. In calculus, it's our first clear example of a function with jump discontinuities, which lets us practice left-hand and right-hand limits. Later, when you study integration, you'll see the floor function pop up inside integrals to count whole units, and in series to group terms by integer parts. Let's look at the staircase closely. The output of the floor function is always an integer, so its range is the set of all integers. On each step, the left endpoint is a closed dot, meaning the function includes that point. The right endpoint is an open dot, meaning it does not. So each step covers a half-open interval like from 2 to 3, including 2 but not 3. At every integer, the graph jumps up by exactly 1. Because of this jump, the left-hand limit and right-hand limit are different. The limit as x approaches an integer from the left is that integer -1, while from the right it's the integer itself. Since they don't match, the two-sided limit does not exist at integers. Imagine a simple tax system where you pay 10% on the first 50,000 rupees of income, and 20% on anything above. The tax you owe jumps at the 50,000 mark. That jump is exactly the kind of step the floor function models. The ceiling function is its twin, rounding up instead of down. And if you take a number and subtract its floor, you get the fractional part, the little leftover after the decimal. For 3.8, the fractional part is 0.8. These three, floor, ceiling, and fractional part, work together. In advanced calculus, you'll see the floor function inside integrals to some areas step by step, and in series to handle terms that repeat over integer intervals. The whole idea is, the floor function turns continuous numbers into discrete steps, and that simple idea unlocks a huge range of real-world and calculus problems.